Welcome to this end of the week, Friday, where we have a lecture on a new topic. Looking at the numbers of the students coming in, I think there's still a lot, half the class are not here yet. Let's wait for a short while I'll set up the system. While waiting for the rest to come in, to numbers to reach a decent number, are there any questions that you might want to ask? No? Okay. Let me set up the PowerPoint and we will start very soon. Okay, we're all set to go. So this will be the last topic in the field of artificial neural networks. So as you can see, this is one of the newer topics because I think with the media reporting the various success of artificial neural networks, in particular deep learning. So we have already added this in. This topic basically is an introduction. More of the, not so much as the, what we call the practical aspects, but more of the theoretical foundations. So we will, and you can see later on, it is just basically an extension of the topics that we have. We have actually we studied two of the models. The first one is the feed-forward, which is your multi-layer perceptron. And then the next one, we move on just about in the middle of this week. We actually finish the one on the recurrent networks, in particular, the COPUNet. So let's go into this particular topic. And I feel that after reading this in one of the magazines, the IET, the UK-based global professional society for engineers, in particular electrical electronic engineers, I feel that I should share with you. This is quite an inspiring quote from the late His Royal Highness Prince Philip, the Duke of Edinburgh. Right? Everything that wasn't invented by God is invented by an engineer. I think this is very true because most of the modern inventions, I would say, some form or another, they are invented by engineers. I think most of it, if not all of it. So, what do we hope to achieve? What do we hope to learn from this particular topic, from this particular lecture? So you can see here, there are actually four main points that we hope to achieve as the outcome of this topic itself, of this lecture. Hopefully, we can finish most of it today, if not all of it. Right? And then we move on to the other parts. This one has two parts. The first part is just a basic introduction, the motivation, and the challenges of deep learning. And then we also look at some of the common deep learning models. Of course, I think we look around you, there's actually just a small handful as compared to the general field of artificial neural networks. So we will look at some of the more common deep learning models in more details. Then we look at the applications of deep learning. Again, of course, we will not cover that even as we speak today, as we speak now. There are somewhere in the world, someone actually looking at the different applications of deep learning. Because we want to push the boundaries to see what can it do. Right? Since it's has shown great success in some of the other applications, it is something else you can do. So we're trying to someone somewhere is trying to break the boundaries, push the boundaries, and then see what is the level of achievement in deep learning. So remember, those of you actually saw the video last week. We showed basically how the AI in general has been successfully used in actually harvesting strawberries, in harvesting what do you call it? They call it bell chilies, is it? Or something like that. Capsicum. I think basically I know them as capsicum, large chilies. So harvesting, and there was a major effort, because when I look at the team from I think 2 or 3 different universities, and then from 2 or 3 different countries, right? The Netherlands, the Israelis, and also one company who is the industry partner of this collaboration. So this is some of the applications. So maybe when you start to work later on, just next year, it's not too far away, right? When you start to work, you'll maybe come across some of the newer applications of deep learning. Or even as we speak, some of you with the supervisor is trying to see what are the things you can do with deep learning. So let's look at the motivation for it. So in general, if we look at the area of machine learning, right? It has been suggested that it has been pretty much stagnant, not much major breakthrough, right? Since the 1950s. If you look back to our first few lectures, we talk about the history of AI. So at that point in time, you can see that there was some major achievement, right? In terms of making at that point in time small breakthroughs, but since then it's more or less pretty stagnant. But again, I think with I think it wasn't much publicized. Let me put this way, publicized or marketed. So the industry was a bit hesitant in terms of investing money into AI. But now, turn the clock, fast forward to 2021. Now, for those of you who have been looking at the papers, newspapers, you find that in Malaysia, they were talking about what? They're talking about having an AI park, artificial intelligence park, and just nearby, Technology Park Malaysia, TPM, which is next to the Stadium National, right? That area there. They want to do a AI park. They want to group together companies who are researching, who are developing products, developing tools in AI at that site, at that venue of TPM. So the first learning machine, the PERCEPTRON, right, was built at Cornell University, Cornell in 1960s. So remember at that time that I think we talked about this before, and we're looking at this. Now, we also have been looking at it in terms of the shortfalls, as well as what it is able to do, its capabilities. So basically, the PERCEPTRON was a linear classifier on top of a simple feature extractor, right? So what is meant by feature extractor? Feature extractor, we look at the picture over here on the right-hand side here. What it basically shows is that you have a letter A. So from the letter A, you want to extract the characteristics or the features of that image itself. So as I said many times in my lecture, so if you were to identify apples and oranges, a simple example, apples and oranges, you want to extract some of the main features which you think, okay? Again, you look at it, the human have to decide what you think are the major features, main characteristics that I can extract. So I will extract the color of my fruits, right, of that image, and maybe the texture, because you look at it, unlike the apple, the orange's skin is not smooth. It is, like we said, consisted of bumps and valleys. So those will be some of the features you extract. So this is what you mean by feature extraction. So feature extraction, you extract the features, and then from there you pass it to your classifier. This is in this case a PERCEPTRON to separate, right, especially if it is linearly separable. It means that two classes based on the features can be clearly seen by drawing a line to separate the two. So that is what is meant by feature extractor. So the feature extractor, some of you are doing some work there in this semester. They're trying to identify a few things, but basically using the old classical method of features rather than using images. You see why it has pros and cons. It's not how do we say? Your deep learning is not the magical silver bullet that can cure everything, can solve all the problems in the world, right? There are some shortfalls too, as some of you may, not some of you, some of your seniors have found out through their disappointment. They find that the deep learning classifier, deep learning network, wasn't able to even identify simple things based on the color. So it only achieve about less than 50%, right? I always say that if your accuracy is less than 50%, compared to if I were to just get a coin and toss a coin, right? A coin hits is, for example, grade A, and then tail is not grade A. So I can use that simple method without having to spend time and money in designing and developing a deep learning network. So as you can see later on, there are some shortfalls, some of the weaknesses of the deep learning. So the feature extraction cluster method is still acceptable, is still attractive enough for some of us to actually work on that. Now, going to the next point, the vast majority of practical applications of machine learning today use glorified linear classifiers or glorified template matching. So based on a certain template, you match on the new data that you have. Now, designing a feature extractor requires considerable efforts by experts. Fair enough. To actually extract the features of this image here, it needs certain what do you call it? It needs skilled people, right? Skilled people, and not everybody can do it. So you need the experts to actually tell you what are the first of all, what are the features you want to extract, and then from there you have to design the software, the software of the tools to actually create or extract those features. Right. So those are some of the motivations for the has resulted in what we know today as deep learning. Now, pictures here below, actually on the left hand side, shows you, I think, basically someone actually trying to extract, right, with lighting here to extract the letter C. And here is probably one of the early computers, which is actually less powerful than what you have today, even on the handphone. I can see a lot of wires, the room of transistors and valves to actually do that. So this is an example of someone maybe trying to solve the problem of the computer breaking down. So you actually pull up some of the valves, some of the equipment inside, some of the components inside this early days computer. So this is quite a very busy slide there, but let me quickly go through and try to explain some of the key points here. So if you were to view an image as a one-dimensional vector of features, right, or simply so you have to view an image as a one-dimensional vector, right? Because basically you look at it, even for this image itself is two-dimensional, but you can actually convert that into a one-dimensional vector. So basically, we are trying to view an image as a one-dimensional vector of features, x or pixels, if you like. So therefore, your image classification, which is what you did before, this is grading, for example, and recognition. You need to classify. This is an apple. This is an orange. At the same time, from there, you can then recognize this is apple or orange. So therefore, the image classification and recognition then becomes a machine learning application of FFX. So if that's true, then come back to the old way of doing things, which is the features. You have to decide from your analysis, right? What are the good features? I can see from the lab, from the assignment report, many of you have tried to actually put in effort to actually do a good job at analyzing the data. So of course it is tough, right? It's not easy. I also understand that, but it's a good training. You can see that some of you have actually put effort to actually try to analyze the data and try to explain your analysis of those data. So the question is, what are the good features? So I think some of you actually tried in terms of what do you call it? You were given 4 features, right? So some of you felt that after the analysis, you do not want to confuse your fuzzy logic system or fuzzy expert system by confusing it. You're using 4 features. Some of you actually use 1 feature or 2 features, and those results were pretty admirable. Quite good results were achieved. Then comes the question. Now, of course, there are 2 ways of doing that. One is unsupervised learning. So in the case of unsupervised learning or unsupervised classification, you were given examples x of I of a random variable x. So you have many features of that random variable implicitly or explicitly. Then we learn the distribution probability of p of x or some properties of p of x. So from there we learn, right, based on the features and what are the features that's going on. So some of the methods you can actually use actually is these are very what they call basic and old or classical unsupervised methods. You can also actually use that to actually reduce your size of the vector. Imagine if you have a few thousand features, you can actually only use a few thousand, or you can also even for 4, right? As we have discussed in either the lecture or the tutorial, we have seen it is virtually impossible to show 4 features, draw 4 features on the piece of paper, because you cannot do that. First, 4 dimension you cannot reduce to 2 dimensions, so it's virtually impossible. But if you can use this technique called PCA, which means principal component analysis. Basically, this method is very clever, right? It just reorganize your data. Even if you have 1,000 vectors, 1,000 features in your vector, 1,000 components of vector, right? 1,000 is definitely impossible, right, for you to draw on the piece of paper. But based on this principal component analysis, you can actually reorganize, or after calculation, right, after we calculating the 1,000 features, it will then order the most important at the top, and then in a decreasing order, right? Most important, less important, so on and so forth until 1,000. We still get back 1,000. Now, if you have that, if this is sorted or arranged in this order, what does it mean? It means that I can then pick the top 2, because if they are so important, the top 2 should represent at least maybe 90%, if not 100%, or 99% of the important of the whole 1,000 vector, 1,000 features vector, right? So if I pick the top one and the next one, so I will cover in general most of the important features of my vector. And then from that, I can then draw onto a 2-dimensional space. So from 1 dimension, I can then reduce to 2 dimensions to draw. So for visualization, I think many of you actually see the power of visualization. Maybe some of you do not notice that. May not notice that. Why? When you actually analyze even your simple EBN assignment from 4 features, right? Many of you actually use figures to explain, and that is a very powerful tool you can use in AI. This is called visualization. So for PCA, you can actually do that. Same goes for your k-means clustering. This k-means clustering is based on the data that we have. I want to order them, I want to arrange them, who belong to what, in terms of user specified k number of clusters, right? If I have, for example, I have 1,000 pieces of feature-based representation of my apples and oranges, 1,000. Let's say based on maybe even just five features, right? The color, the weight, right? The texture of the skin, right? The shape, and maybe the acidity. The acidity, we actually measure the acid level or even sugar level. How sweet are the two objects? So if it's 5 features, I want to, based on the training data, I want to see which one belongs to what. So from that, I can find the centroid. I think later on we come to that later on in the next few lectures, especially in the support vector machine, we talk about the centroid and also a bit of k-means clustering. So given in the unsupervised machine learning method, so we are given a set of training images and labels, then we predict, right, the labels of a test image without any supervision. We just say that we train it with this data. So this training or machine learning method, either based on PCA or k-means. K-means the user only specifies how many classes I want. So in the case, if I know that I'm only looking at apples and oranges, I will select that 2 classes. I will select 2 classes. So from there, I will then, after the method or the algorithm has converged and stable, right? Converge to some good stable answers. I will then use that to test it against my something new that I've not seen before. So this is basically the essence of the main idea behind unsupervised machine learning. So far, so good. Any questions, comments? Still, a large number of you have not logged in yet. I see numbers, 74 probably, 74, 75, 74. So another 10 plus have not signed in yet. Now, in the case of supervised learning or supervised machine learning, you are again given examples, right? A set of examples and the associated labels. Now you are given the labels that this piece of data is an orange, this piece of data is apple. So it's labeled what we are given in the assignment that we just completed recently. Then we learn to predict a label from the actual example data, right? But usually by estimating the probability of x and y given that x is true. Remember this is our conditional probability statement or probability representation, right? So again, we can then use something some of the simple methods. This is a KNN, which is a k nearest neighbor. So in this case, it's slightly different from your k-means. So I want to see how many, if I select k equals to 3, I want to see who are the 3 nearest neighbor to that particular point, right? So this is a k nearest. So some, of course, if you want to use a k nearest neighbor or even your k-means, you need to have some sort of a measurement of nearness, how near is that object from the current point, right? So this is you need to use some sort of a distance metric to actually be able to complete or calculate your k nearest neighbor. And then of course the hyperparameter k, which is actually user defined, right? And this is actually method is slow because of the curse of dimension, and it's actually not linear. Now, if you were to search the term itself, the sentence itself, which is something new today, the curse of dimension, because if you're doing AI, right, or any other similar field, you find that you're always I won't like to use the word curse. It's actually somewhat strong. You're actually constrained by the dimension of your data, right? And again, you'll see later on what does it mean. But of course, this one, I think we've seen some indications of that during our lecture on the traveling salesperson problem, right? And I think I told you before, I was running some simulation to actually try by exploring all the possible combinations, right? Let's say I have 10 cities or 13 cities to visit. So I want to try all the various combinations. First of all, I go to Ipoh first. Then the next one, I try to go to Johor Bahru first, or Malacca first, or Serangoon first. You see, I'm trying all the various combinations, right? And then after I finish all my 13 cities, I then calculate what is my total distance travel. We can stop for a while. Okay, I'm back. So if you try that and all the possible combinations, you can actually work it out, right? As you've seen before, is 13 factorial over 2, I believe, right? Oh no, sorry, 13 minus 1 factorial over 2, right? So you can see the huge number of routes or paths or solutions I can investigate or explore. I started this work on Monday, and today I checked my results on my computer. It's taken 2 days and a few hours to complete. Right? Imagine that your PC is running on for 48 hours and 48 or 50 hours plus, right? Just doing nothing but calculating. This is only on what 13 cities. So this is a one example of the cursor dimension, because it will scale up your calculations non-linearly. So from this, we then look at from such a simple methods, which is your K nearest neighbor, either your PCA or your K-means clustering. We then look at this to the non-linear neural networks, which is what? Which is your multi-layered perceptron, multi-layered neural networks, and then for example, now we're talking about the deep learning. So neuron as a linear classifier, right? A single neuron is a linear classifier, as we've seen before, right? The decision function is inclusion function. So this is your standard equation for your linear classification, or equation for your perceptron or your simple neuron. Basically, it is a dot product of two vectors, and it's a scalar product. So basically, some have said that it's a template matching or correlation, whereby the template W and input vector, right? You're trying to match that, right? So this one, if you look at it closely, this is what? This is your representation for weights, right? And X is your input. Also, some have said that it's also an algebraic distance, not the geometric one, which is non-linear. So therefore, the solution is that if it's a non-linear, right, then the answer solution of course will be non-linear. Now, moving along, the dot product is a metric distance of 2 points, one data and the other is a representation of that space. It's also an angular distance, x dot w equals to the magnitude of the x multiplied by the magnitude of w, then your cos theta. Theta is the angular distance, angle between x and w, whereby the true distance actually, this is your true distance, taking the magnitude of the square of the x minus y, x minus w, equals to cosine law and cosine. Now, the linear is that the decision surface is linear. Basically, we've seen that before in the first lecture on neural networks. It's a hyperplane. So the decision function, it's not linear at all. So to find that surface is actually not linear at all. Right? We're still looking at the motivation for the for some of the problems that we face in the method so far at that point in time before the emergence of deep learning. So now we're looking from linear to non-linear classifiers. Right? We've seen that, and therefore we are going for the multi-layer now. Multi-layer neural networks, because the single layer, right, the perceptron cannot handle non-linearity. Only non-linear, only the multi-layer perceptron or multi-layer network can handle the non-linearity. So basically, you need to go for multiple layers, right? Go higher and linear. So what does it mean? It means that you're trying to find a map, mapping or transform from x into phi x to make them linear, but in a high dimension. Right. So this one may be a bit challenging for some of us to understand, but basically it means that from a simple x set of data, we're trying to transform the high, what you call it, transform into high dimension, but still make them linear, right? So basically, it's a complete basis of polynomial and too many parameters to be limited. But in doing so, you find that there are too many parameters for the limited training data. So One of the methods you can use. You can use the kernel methods and also, for example, support vector machines. This is our one of the topics we will look at in the next few weeks. Support vector machines. Actually, it's a very clever way of doing things. Right? From a non-linear problem, you try to convert back to a linear problem. Therefore, you can use some of the simple methods to actually find the answer to that non-linearity problem, non-linear problem. That's why we look at this. Basically, that is the trick involved in most of the field, most of the applications. You convert, you see a similar problem that it can be parked under the similar class of problems, then you use back the tools which have been shown to be successful in solving such problems, that class of problems. So you basically learn the non-linearity at the same time as the linear classifier. So you basically, in this, when you map to a high dimension, right, you still use back the same technique as those linear classifiers. So this is your multi-layer neural networks. So what is new, right? MLP is not new. I think we've seen it before in the previous lecture. We find that this has been around since many years before, right? So MLP is not new. But notice what they say here. Your deep feed-forward neural network is modern. Not new, just modern, right? And it's still your feed-forward. So it is similar to your MLP, as you see later on, and you will see the differences as we go back. So it's feed-forward, right? This is again just to emphasize, it's a feed-forward. Your deep neural networks, is especially if you use a feed-forward type, it's actually feed-forward from X to Y, no feedbacks, right? So basically, networks, they are modeled as a directed a cyclic graph for the composition of functions connected in a chain. Now, the depth of the network is n. So basically, the only difference is that this n here is actually much larger than your simple MLP. MLP that we studied so far is actually based on only one middle layer or one hidden layer. As you see later on, the number of middle layers here can be quite large. So your deep learning basically means that your n is now increased to some significantly larger number. Okay. So now let's look at the motivation. Now, so with that background of the problems or challenges facing at that point in time, before the 90s, the classical methods of AI. So one of them is actually, as we've seen before, is the curse of dimensionality. Now, so what is it? What is in deep learning that can overcome such problems? So the core idea in deep learning is that we assume that the data was generated by the composition factors or features potentially at multiple levels in the hierarchy. Basically, this is the core idea of deep learning. We assume that the data was generated by the composition, so it's a combination of different features, right? Multiple levels in hierarchy, hierarchical organization of your features. Now, based on this assumption, so therefore this assumption allows an exponential gain in the relationship. So because of this assumption, it allows you that exponential gain in the relationship between the number of examples and the number of regions that can be distinguished, right? If you have many examples, your examples mean what? Examples means your training examples, the data that you show to your deep learning network, right? And also the number of regions, how many classes, right? So you can have, for example, I want to look at what people are doing in a normal scene, normal picture. If I take a picture, I'll take a video of a busy area. Say, for example, last time, the old days, you can just put up a camera and take a picture of our canteen too, right? Canteen too, and see what people are doing. So from the video, which is 25 or 25 frames per second, right? You can have then many examples. From that, you train your deep learning network to see what people are doing, right? This is some of the things we do in trying to understand or what we call scene analysis, for us to monitor public space or public spaces, right? This can have a very useful application for the police and other enforcement agencies to see what people are doing. So as a result of that, now if you look at it, a simple video data of a simple scene, I can then have many examples, right? From the if I were to process each frame by frame, I will have many examples for me to train the system. I can also have from there, I can also can train the system to identify whether people are sitting down to eat, what are they eating, right? And then are there people standing around waiting for their food to be cooked? So this will be the number of clusters of which of the actions for that simple example. Now, the exponential advantages conferred, right, as a result of the use of deep distributed representations counter the exponential because they overcome the exponential challenges posed by the curse of dimensionality. So basically, if you look at this statement here, basically it's saying that when you increase your dimension of your data, right, it is not a linear, it's not one-to-one, it's not a linear increase in your challenges. It will be exponential increase in your challenges. So you can see basically it's saying that when you have more and more data, more and more features, you find that the increase in the computation increases exponentially. It's not linearly. Right? That's why I give you an example of the traveling salesperson from TSP. When you increase from to just 13, right? If you try it out for 5 cities, it will probably take you, if I do it by hand, pen and paper, it will take you maybe a few minutes to do it. But if I increase it to just nearly 13 cities, I find that the actual time involved is not just multiplied by the earlier time that I spent for 5 cities. It is exponentially increased to 2 days, a few hours. So 48, 50 plus hours just to do that. So you can see that it's an exponential increase. So let's do a quick visit to what you mean by curse of dimensionality. Now, the curse of dimensionality refers to a set of problems that arise when working with high dimensional data. Many features, right? So imagine if you were to give you an assignment tomorrow, not on 4 features, but maybe 10 features. You find that you take a long time for you to figure out how do I solve this problem of just nearly 10 dimensions. Now, the dimension of a data set corresponds to number of attributes or features or characteristics that exist in the data set. So again, example will be from the traveling salesperson problem. The features will be for 5 cities, it's just 5. 13 cities is 13. Now, those will be the features of your data set. Now, a data set with a large number of attributes or features, generally of the order of 100 or more, is referred to high dimensional data. So this is a very loose and informal definition for what you mean by high dimension data. Right? It's just 100 or more. Anything more than 100 will be considered as high dimension. So going back to our earlier example of just 13 cities or 10 or 16 cities in our lab number 2, right? The lab as practical number 2, you find that it's not even considered high. It's still considered very low, but the amount of time that you actually need to solve it, especially manually, is actually very challenging indeed. So some of the difficulties that come with high dimensional data shows itself during analyzing or visualizing the data to identify patterns. So when you're dealing with high dimension data, right? So in this case, we're looking at 100 or more. You have challenges in either analyzing or visualizing. How do you analyze 100 dimensional data, 100 features, right? And also at the same time, some of these challenges or difficulties will show itself when you train your system, when you're using your AI method to train your AI algorithm. So the difficulties related to training machine learning models, whether you're using artificial neural networks or using your Bayesian, things like that, is actually due to this high dimensional data. And such difficulties is referred to as the curse of dimensionality. This is something quite common and well known. So what are the two common aspects of this curse of dimensionality? It is data sparsity and distance concentration. These are two of the common, in terms of how the data is actually show itself in the n-dimensional space. This is your data sparsity, and of course the data distance concentration. How concentrated are your points of the data that you have in your data set. Now, what is data sparsity? So supervised machine learning models are trained. So we are going back to the example of your supervised method, or even unsupervised methods, which is machine learning, ML, or AI. I train to predict the outcome of a given input data sample accurately. So we actually train your system to recognize certain data and then accurately. Now, while you train a model, the available data is used such that a part of the data is used for training the model, and a part of data is used to evaluate how the model performed on unseen data. Now, this is something most of you did not do in your assignment. I say most of you, some of you did it. That means you actually partition. You partition your data into a training set to train the model, and then the other remaining data that you did not use is now used to evaluate how your trained model will perform in such unseen data. Now, some of you do it once. You partition your data into training and test data, but only once. Now, my question is, if you do that once, how sure are you that if you use the same model, if you were to sell your system to someone else, assuming even it's on the same data set, for example, apples and oranges, right? That person, you say that, hey, look at it. I managed to train my system, and my system is able to achieve, I think some of you achieve 100%. 100% accuracy, which is fantastic. Well done. Now, if that 100% accuracy in terms of the prediction of new data, now you manage to convince someone else to use it on his or her own data set. Similar, let's say it's still apples and oranges, right? How sure are you that he or she will get that 100%? Because your system has not been tested well enough. What do I mean by that? It means that you also need to randomize. Okay, based on my data, I will now take another set of data for training and then test it again on the remaining set, and I'll do it a few times. Different combinations of training and testing data. They will give you a more robust in terms of the testing your performance of your system. Right? Now, such evaluation of training and testing will help you to establish whether the model is able to generalize. That's what I meant. Because if you were to use your system somewhere else on a different set of data, even on the same problem, apples and oranges, right? You are not generalized. Maybe it's not generalized enough, right? So I think I will be very worried, a bit uncomfortable if you say your system is able to achieve 100% based on your sample of training and your sample of testing, because you have not randomized it enough, right? And test the generalization ability of your system, of your model. Now, unfortunately, as the number of attributes or dimension increases, the features increases, the number of training samples required to generalize a model also increase, not just linearly, but phenomenally, exponentially, right? So you also need more and more training samples to be able to, especially if you have high dimension, 100 different features, right? To actually be able to convince people that your system is actually, your model is actually generalized enough and can give you this accuracy of 75%, for example. So this is basically explaining about data sparsity. Continuing, I'll quickly run through. So in reality, the available or training samples may not have observed targets for all combinations of the groups. I think most of you actually recognize that. Many of you are in your conclusion section of your report. Most of you, if not all of you, actually understand that. You understand that the number of samples given to you, 63, is insufficient, right? Insufficient for you to conclusively say that your method actually works. But don't forget that I will talk about that later on. Now, the training samples given to you normally are not enough, right, to tackle all the various combinations of the attributes. Now, this is because some of the combination occurs more often than others. Right? Notice some of the patterns in that set of data occurs more often than the others. Due to this, the training samples available for building the model may not capture all the possible combinations. What does it mean? It means that your training data or your data that is collected somehow is skewed towards certain attributes, certain types of apples. If you go back to our example, apples and oranges, right? It's skewed. It is actually more concentrated on some patterns, not all the patterns. So some of the possible combinations, but not all the possible combinations. Now, this aspect where the training samples do not capture all the combinations is referred to as data sparsity, or simply sparsity in the high dimensional data. So it means that your data actually is not sparse enough. It's actually heavily concentrated on certain aspects of your data, of your data itself. So training a model with such sparse data could lead to high variance or overfitting. So it's actually learning only certain type of apples or certain type of oranges. It's not able to capture other types of apples to learn about the variations in the other apples, right? Because your small training samples. Now, this is because such thing occurs because when training the model has learned from the frequently occurring combinations of the attributes. So you only see the more frequently occurring patterns, and therefore can predict the outcome accurately. So maybe for that, for those of you who actually managed to achieve 100% accuracy based on your fuzzy logic system for the assignment, maybe your data that is selected for the training is actually skewed, right? Concentrated to something quite simple for the fuzzy expert system to recognize, right? So it's able to predict the outcome on the unseen data now accurately, which is 100%. Not even one making even one mistake, all perfectly done. Now, in real time, when the less frequently occurring combinations are fed to the model, it may not predict the outcome accurately. So in practice in real life, when the system comes across the less frequently occurring combinations, right, your model then will not be able to predict the outcome accurately. Now let's look at a bit of what we mean by distance concentration. Now, distance concentration refers to the problem of all the pairwise distances. So A versus B, A versus C, these are the pairwise distances from different samples or different points in the space, converging to the same value as the dimensionality of the data increases. Now, several machine learning models, AI, such as clustering or nearest neighbors methods, use such distance-based metrics, right? Actually, your k-means and I think we look at the no, we didn't look at that. Your TSP, your traveling first person problem, the HopFuNet also uses distance-based metrics, right, to identify similar or close samples near to the current point. Now, due to the distance concentration, the concept of proximity, nearness, or similarity of the samples may not be qualitatively relevant in high dimensions. So, due to this distance concentration, right, of this pairwise measurement of the distances, when you actually increase it to high dimension, right, may not be relevant. Such measurement of distances may not be relevant in high dimensional data. So let's look at the examples here, right? Now the examples here, the graphs here, the figures here show the distribution of a normalized distance between different samples in different dimensional space, right? Now, in this case, a fixed number of random points were generated from a uniform distribution of D-dimensional torus data. This is a torus. The D here corresponds to the number of concentration considered at the time. So this is 1 dimension, 2 dimension, 3 dimension. Oh, sorry, 1, 2, 4, 8. Then when you have here, you can see here. Now, when you have 1 dimension, it's quite equally distributed because it's a uniformly distribution, the data itself. Now, with a 2 dimension, you find that when you measure the distances, what do you call it, the normalized distances, you find that it's no longer so nice. So you can see here as the dimension increases from 2 to 16, 32, 64, 1 to 8, you find that you have only the data is concentrated in certain regions. There's a lot of empty space here. So these are what is meant by this is a visualization of your distance concentration. So for the 1-dimensional torus, you see that this density is approximately uniform. Now, as the number of dimensions increases, we see that the spread of the frequency plot, how frequently the features of the certain data occurs, decreases. The spread, the width of your spread of your data decreases to just a narrow band here as the dimension increases. So if you were to plot against the dimension on the frequency, you find that it's actually non-linear. As the dimension increases, you find that actually it drops non-linearly down here. So this is one of the other aspects of your curse of dimensionality. So now, with that long introduction, now we come to deep learning and what it is supposed to overcome some of those things we talk about in curse of dimensionality and high dimensional data. So what is deep learning? So this is one example. I want to caution you. This is only one definition of what is deep learning. So deep learning is a branch of machine learning that uses data and loads of data. This is actually emphasis, not just any data, but loads and loads of data, a huge number of data to teach the computers how to do things only humans were capable of before. The machines solve the problems of perception, recognizing a face, right? So here, notice a face actually is a partition into regions. Using this, you can see here on your screen. This is actually partitioned into a grid, right? So here, I think we'll try to measure the size of the mouth, the width of the mouth, where is the nose, where are the eyes, things like that. This is feature-based. At the same time, we also want to learn. We want to also imitate how the humans recognize speech, audio signal, recognizing it. Who says what? So let's do a quick revisit of the history of neural networks, in particular deep learning. So you can see here, we actually, Frank Rosenblatt actually created the perceptron in 1958, long time ago. And actually, some have said that this is actually an algorithm for pattern recognitions. From there, it's taken about what? For 31 years later, only then, right, the scientists were able to create algorithms that use deep neural networks. I think at that point in time, 1989, it wasn't seen as deep learning. And again, at that point in time, there was no excitement in terms of, wow, this deep learning can do such wonderful things. Because at that point in time, the computing power is actually still relatively slow and also quite expensive. So, you don't actually use, you don't train your system for your neural networks for days and months or weeks to do something. So those things, even if you take 1 week to train your system, it's not, it's still solving a small problem, low dimension problem, not a high dimensional data problem, right? So only until 2000s, in the late 1990s and early 2000s, the term deep learning began to gain by Geoffrey Hinton. Geoffrey Hinton, I think, was a neural network scientist in the 90s. but only at that point in time we actually proposed this deep learning. So in 2012, 9 years ago, the artificial pattern level performance on certain tasks. At that point in time. So we actually use the neural networks, right, and to recognize certain things. Match human capability only in certain things, not everything. So as I said before, we cannot recognize music and at the same time recognize faces, right? So those are two different fields, but humans can do it quite well. So only at that point in time, that's where people get excited about this achievement, which is your AI method, your AI algorithm, your AI software can now match the human performance. That's why a couple of years ago, when we have this big hoo-ha about this AlphaGo, able to beat, right, the human player in the game Go. So going along, try to explain more what you mean by deep learning. So this is the traditional method, right? As I said before, feature-based. So you have this is a picture you have, and then from there you actually try to extract the characteristics of this picture for you to recognize cars, right? What is the percentage of the size of the object there? What's the shape of the object there? So this is what we call feature extracted. So this is handcrafted. You have to design the relevant features. Car, the yellow car in a field of in a football field, for example. Now, compared to deep learning, this will then learn representation or learn the features. So this will be you train the deep learning network will actually have a trainable feature extracted embedded inside your deep learning classifier. So here I do not need to do a handcrafted feature extractor. I do not need to manually design a feature extractor. So this is all inside my deep learning. So when you do your deep learning network, you find that I do not need to extract features. So this is just throw everything inside with a deep enough network. The network is able to extract the relevant features for it to tell you what is this? Is that a car or a bus or whatever? So this is all inside one deep learning. So deep learning is also about learning hierarchical representation. What do you mean by that? So that's why you have the deep learning. You have multiple layers, right? It is deep if it has more than one stage of non-linear feature transformation. Now, look at the pictures here. So at one of the earlier levels, earlier layers of your deep learning network, it learns this. It learns about low-level features taken from these 2 or 6 by 5, 6 rows and 5 columns to learn this picture low level. Then from there, this is a pass to the next layer, and this is actually learned from here. It learns another layer learns this. So this is the mid level, and then it goes past to another layer, the high level. So after this, you find that right this trainable classifier done automatically. Manually train, extract your features. Now, this is from a paper by Ziller and Fergus in 2013. And this is a feature visualization of convoluted net trained on ImageNet. So this is a paper, and this is how they show, they actually explain how the deep learning network works. Okay, I think I'll stop here for a while, take a break, and then we'll come back and then look at the next partner of the this introduction to deep neural networks. Question before I take a break? Okay, anyway, if you want to chit chat also, I'm okay. I'll be here. Okay, I'll take a short break and I'll say about 5 minutes. Okay, I'll start very soon. Okay, now basically, what have we seen so far? So we are looking at the trainable feature hierarchy. Now the earlier slide here, deep learning will learn the various features in a hierarchical order. So at the you learn the, first of all, the low features, and then you learn the middle layer features. And then before it passes to recognize what each of these is supposed to represent, this pattern here. Look at it, basically when you have such a hierarchy of representations, right? It actually have a, over here, you can see here, right? There's an increasing level of abstraction. So actually extract from here, the car itself, you can see here, or rather not the car, the scene, which has a red car and a yellow car. So it's extracted low level on its own. Then from there, it will actually process such low level features into middle level features. So this is your increasing level of abstraction. Right? You can see here, actually it's a transform this image into this kind of features, and then from this kind of features again transform into another level. So for image recognition, it will be pixels, right? Right? Pixels, edges, is the part undefined object. Now, if you do the same thing for text recognition, right? Words or printed text. First of all, you look for characters, then you look for words, word groups, the clause, the sentence before you tells you the story all about based on these characters and the words. This is the final output. Same goes for speech. You have a sample of the speech, your spectral band, your sound, and then of course there are many different layers, your phone and the phoneme before it comes to your word. You can see here when you have layers here, each layer will represent, will learn. The layers will be trained and then perform the feature transform. That's why I think you can sense that we are moving towards that. That's why we have this multiple layers. Each layer again doing some of transform of the initial pattern that we have, whether it's a speech, whether it's a text, or whether it's an image itself. So how do we, and then what are the challenges in learning representation? How do you learn, right, the features itself, right? Learning representation. How do you learn the representation of this picture from here, and then from here, how do you learn this representation of the first first level and then into the next level and so on and so forth. Right? So how do we learn represent? So some of the challenges will be how do we learn representative of the real world, right? By looking at the world. How can a person AI build itself by looking at the world? Let the system learn on its own, right? Build its own, build itself. How do we refine itself? How do we change itself, the system itself, by looking at the world? You just throw in the pictures of the world. How much prior structure is necessary, right? So you can see here, these are your network to actually learn the features. Now, in terms of machine learning or AI, how do we learn features or feature hierarchies? It's a fundamental principle. What is a learning algorithm? So these are questions you need to ask, because in order to develop or design a useful and accurate system that can learn all these different representations. So the next one will be in terms of in area of neuroscience or even in terms of cognitive science. How does the mind learn abstract concepts on top? From the cognitive scientific point of view, you want to study how does the mind learn the abstract concepts on top of less abstract ones. So simple concepts into more difficult or more complicated abstracts. So the answer to that is that the deep learning, your perceptual system or artificial system, addresses the problem of learning hierarchies with a single algorithm by having multiple layers. So that is I think they found out that that's why we need to have deep learning, because deep learning will be able to each layer will be able to learn that they have in the previous pattern in a hierarchical order, right? Because just a single algorithm or single network itself. So again, let's go back to the to compare. Let's look at the traditional. So this is the so-called the modern architecture, as late as from 2006, from the earlier years, you have your when you want to recognize objects, you have your fixed and then mixture of unsupervised methods and then the supervised methods, right? So this is a representation of the say your audio signal from sound, and from there using something called MFCC, which is a fixed method of learning, and then you use unsupervised, and then you pass the outputs to your classifier. Now, in the area of image processing or computer vision, going back to our picture of a car in the field, we use fixed levels at a low level, extracted. What is scale invariant feature transform? Basically, you transform. Right? This is a very powerful method that teaches. So, or we can also use hop. Hop histogram of the orange. This will then extract mid-level feed. And then you look at your supervised classifier to tell you what this picture is all about. Or some elements of it anyway. What is not the complete list? Level accuracy, combination of SIF or HOP or K-meter. So there will be other variations of such method to actually give you a good answer, accurate answer, scene analysis. Now, this is I won't even bother going to this because this will show you that how the it shows you the breaking. That one I can't do from the office in the campus. So I'm actually using the campus line. I'm not using my own line. So own line I can understand, but this is the campus style using network. So nothing much can do. Sorry about that. We'll try to speak a bit slowly. If I miss anything, I will come back to you. I will speak a bit more slowly. Thank you for letting me know. So I will speak a bit slowly. So this one, as I was saying, this is actually shows you the picture of the mammalian visual cortex. So what is a mammalian visual cortex? That is the brain of mammals, monkeys, higher order, supposedly more intelligent living things. And this one actually is the visual cortex. It's for you to recognize images, recognize pictures. So you can see here, this is a representation, and this was a picture from Simon Top, and it's from that paper by Gallen and Van Essence. So this is actually, but basically what it's trying to tell you is that the neuroscientists have shown that our ability to look at pictures is actually due to the hierarchical organization of the visual cortex, right? So this is just to show you that's why the deep learning actually is based on that principle, based on the human visual, or not human, mammalian visual cortex. I think we have not done it on humans because I think obvious reasons why. So they've done it on other mammals, monkeys and things like that, chimpanzees, for example. So this will give you that to show you that this is actually the deep learning, right? So right on the hierarchy is actually not too surprising, because actually in the nature actually have a hierarchical order to recognize images. So now we're looking at the hierarchical trainable feature hierarchies, end-to-end learning. So we have your end-to-end learning. We are separating. We are separating to having either the sieve or the hop, and then you use it's like a mixed rice. You select what you want. So at the low level, you select your favorite algorithm, which is sieve. Another person will say, I want to use hop, right? So in this case, next level you select K-means. Another person say, no, I will use a PCA, right? So it's like your buffet, buffet of you need to select what you want to actually give you the. So here in such example here, I do not need to select. I will come system. So this is end-to-end learning. So this network here, this system here will learn on its own, right? So with a sufficient number of layers. Now each module or each sorry, my mouse today is quite, I think, funny. Let's try again. Okay, so you can see here, we will transform the low-level features into higher level. So the higher levels, because why? The higher levels features here towards the end here are more global. We actually maybe more global. One way of putting it is that it's not so sensitive to variations in the picture itself. More global and more invariant. Now, low-level features, for example, low-level. What would be an example of a low-level feature? Yellow color, red color, green color. Now, those low-level features are actually not so good for you to train your system, because it is common in any picture, right? If you were to think back, any picture, I can easily find some pictures similar pictures, but which may not have a car inside. Which will have some yellow color or red color. So those are what we call low-level features, and because they are shared by other pictures, shared among other categories, so they are not so reliable, right, for you to use it to classify for your applications. So low-level features are shared among, commonly shared among. High-level features are more unique, right? So more global. So how the question then would all the modules trainable, right? And get it to learn appropriate represent. Now, what here? What do you see? What do you see? You know the names here. You are maybe familiar with some of them, right? You have come across the feed-forward type of neural networks, right? In the one of the 2 weeks, maybe 2-3 weeks ago, we look at the feed-forward type of neural networks. Except now, in this case, sorry, you have many multiple layers, right? So this is one of them. So NLP can also be a deep learning network, and so is your convolutional network. I think we'll look at that in the next lecture. We'll talk about the convolutional neural network. What does it mean? How does it work? What is the architecture of it? Now, if you look at the one with the feedback, right? Of course, we don't have the sparse coding, what do you call it? Sparse coding deep learning networks or the convolutional networks. These are your feedback with some feedback, and they are still deep learning networks. Then you have your bidirectional, deep Postman machine. This one is something we didn't study, but it's a more specialized field, another variation. So in this case, you have the both forward and backward. That's why we call it bidirectional. And also we have stacked autoencoders, right? So autoencoders is also another form of deep neural networks, which some of you may be using in your IP. Now, these are the types of architecture. Then what about the training algorithms? You have your purely supervised ones, right? The purely supervised, you purely supervise the learning of the deep neural nets, whereby you initialize the parameters randomly, then you train in a supervised mode, and then now where do you use it? You use that in practical systems for speech and image recognition when you actually train it when it's actually fully supervised. Now, in the unsupervised training algorithm, right? You have you train each layer unsupervised, one after the other. Then you train your supervised cluster on top, keeping the other layers fixed. So once you train your previous layers to extract the features, then you train then you fix them, fix the earlier layers, and you train your supervised classifier on top. Now the other type of common training algorithm is you use unsupervised, and you have your layer-wise and plus global supervised fine tuning. Now you tune your whole network. So the first step is still the same as before. You train each layer unsupervised, one after the other. Then you add a supervised, then you add a classified layer, and you train the whole thing supervised now. Right? So this is a bit different. This one actually you fix the earlier layers that you train, and then only you train your last layer, which is your supervised, which is your classifier, in a supervised manner. In this case, after you train your earlier layers, then you add the last layer, which is your classifier layer, and then you train the whole system. So this is actually good when you want to look for pedestrian detection. When the label set, when the actual grades or the types or the class is actually not so clear, right? So you're trying to be in the streets. Then the last one is unsupervised pre-training, often uses the regularized output. So when you use unsupervised pre-training, right? The pre-training, they actually use of regularized autoencoders, which is another type of deep learning architecture. So this one is, I think I won't go to you the motivation for your closely. You also, maybe some of you may architecture, shallow neural networks. Once you look at it here, basically you see here, this is the shallow architecture. This is the deep architecture, right? Architecture here, this is removed now. So everything is just one machine or one system. Now, the other motivation is that the deep machines, or when we say deep machines, it's actually the deep layered or deep neural networks are more efficient for representing certain classes of functions. Again, it's not the magic wand or magic or silver bullet can solve everything. Your deep neural networks are only more efficient for learning or solving certain class of functions, particularly those involved with visual recognition. Right? As long if you're dealing with images here can also mean image of your audio signal, speech, right? The speech signal, when you actually record it with a microphone, it can be played back as a visual signal, but it then will be time series. So the deep learning networks will be useful, will be quite good at recognizing such, performing such tasks of visual recognition, right? Because they can represent more complex functions with less hardware. So we need a motivation for deep learning. We need an efficient parameterization of the class functions that are useful for AI tasks. For example, vision, or NLP, and so on and so forth. Now, this is the other motivation for your deep learning. To summarize it, your deep architecture, you trade the space for time or breadth for depth. So basically, you don't have that need for such two steps. For example, you need to extract the features and then you have your classifier. In this case, you trade your space for time. Right? It means that you need to train it longer. Right? Why? Space also means that you need more layers as a result. Right? You need more layers and more sequential computation. But then last hardware, right? There's less parallel computation, since it's still sequential. It's go through hierarchy, layer by layer. So then I think the burning question for us will be, how deep is deep? How do you know my network is whether I'm doing deep or not doing deep network? So again, you can maybe you can sense that there is no subjective. You're only doing two layers. You have the middle layer and the upper layer, right? They are not deep. Even if you train the first layer, because there is no feature hierarchy. Because for the simple two-layer network, you have to extract features to actually throw into your network. You're not throwing the actual image into your network. Similarly, your neural nets with one hidden layer are not deep, right? Some scientists, some engineers, some practitioners, some AI practitioners, people working in AI, also believe that your support vector machines, which we'll see in the next lecture, and the other methods which are known as kernel methods are not deep, right? Because level 1 as a kernel, level 2 would then be your linear classification to actually extract the classes from your first layer. So the first layer is trained with the simplest unsupervised method ever devised, and using the examples as templates for the kernel functions later on. Now, classification trees, another type of method which is actually quite common in AI, are called classification trees or classifier trees, tree structures. They are not deep because there is no hierarchy of features. Right? Again, because this is feature-based and there's no hierarchy of features. All decisions are made in the input space. So before you submit your data to the classifier, the inputs, the actual features are extracted. So there's no hierarchy of features. So the classification method, the classifier there is only to tell you whether this data belongs to what class. There's no extraction of the features, right? As we've seen earlier on, where we actually extract layer by layer into the different various hierarchy in the different layers. So again, so basically, I just want to tell you that this one, I will not go too much into it, but just to tell you, impress you that there is a theory. I mean, those are theoreticians, right? When we look at in terms of theory of the deep learning, it's a nightmare because of deep learning involves non-convex loss functions, right? Because it's not easy to study the theory behind deep learning because they involve non-convex. This is your convex and this is non-convex. Right? How do you study this? Right. So this is some of the challenges if you want to study the theory behind deep learning. So, but then you see, although it's not easy to actually explain from the theoretical point of view of your deep learning, because it involves a non-convex loss functions, but some of the scientists believe that all interesting learning is non-convex, right? Because if it's convex, it's so simple. Because the learning itself is not convex, but it's actually interesting, right? So human learning isn't like that. Human learning isn't about the convex learning. We learn simple concepts before complex ones. So there's a certain order for us to learn things. So the order for humans, the order in which we learn things is often important. It matters. Right? It matters. So this is just to tell you that there are some things which are still not we're not able to find the answer yet, but the deep learning is able to solve things. So, but from the theoretical point of view, they have not been able to understand, right, to actually explain such non-convex loss functions that are common in deep learning. Again, basically there are no generalization bounds. And so the last one is here. This one I want to also tell you, it's hard to prove anything about deep learning systems. If you want to prove the deep learning systems, theoretically, it's actually not easy to prove. Right? But then, right? So basically, I think the other argument is that if you want to prove something first before you want to use them, a lot of those systems, speech, handwriting, visual object recognition systems, are not proven yet from the theoretical point of view. So from the theoretical point of view, those things are not solved. But again, you don't need to prove anything yet before you use that. So they are able to show some good results. But at the same time, we're not able to prove why they actually achieve such good results. So that is the dilemma there, right? For that. Okay. Deep learning, again, this is the final part of some of the challenges if you want to study this from the point of view of theory, right? Deep learning is about representing high-dimensional data, right? So I think from the theoretical point of view, right, I think the scientists believe that there has to be some interesting theoretical questions there in high-dimensional data and how deep learning learns such high-dimensional data. For example, what is the geometry of the natural signals? Is there an equivalent of statistical learning theory for unsupervised learning? So they're trying to map your statistical learning theory to unsupervised learning. What are the good criteria on which to base unsupervised learning? So these are all some of the challenges facing a deep learning theoretician. in trying to understand, trying to explain how deep learning actually represents high-dimensional data. So now let's look at some of the applications. Some of the, I think, the other comment I want to make is that this is actually still evolving on a daily basis, right? So I think next year, if I will come back to this part, you find that some of the things will change. Because as you know, if you look at the literature, the papers published, there are a lot of things being done. Especially everyone is jumping onto the bandwagon. Everyone is doing deep learning, right? Deep learning has been the hottest topic in speech recognition in the last 2 years, right? So, for example, a few long-standing performance records were broken with deep learning methods. What does it mean? It means that in the past, if you don't use deep learning, feature-based, it was able to achieve, say, for example, 80% accuracy. But with deep learning, right, such records were broken. Deep learning methods were able to achieve, say, 90% accuracy, right? And Microsoft and Google have both deployed deep learning-based speech recognition system in their products. Of course, they will not shout on this. They will not tell you that this is a deep learning method. Right? They're using it for speech recognition. Other than this, Microsoft, Google, IBM, Nuance, AT&T, right, and all the major academic and industrial players in speech recognition have projects on deep learning. So, as I said, everybody is jumping into the deep learning, right, because it seems to be able to produce such accurate results. So, other than that, deep learning and computer vision. I think some of you are doing that. But again, be careful in the sense that you might, I think we'll later on to see, is that you need a lot of computing power to actually train your system, right? To train a system in what to do things. And some of you actually are not doing that. You take a shortcut. You're actually using the pre-trained deep learning networks, and then use some sort of refinement to refine it further, refine your trained network for your different application, right? So although it's good and it seems to be able to give you good results, but unfortunately, you may be running into roadblocks that are not able to give you good answers. So feature engineering, right? We've done this before. We actually extract the features. So some call it feature engineering. Is the bread and butter of a large portion of the computer vision community. So basically, we try to extract the relevant features through a process called feature engineering, which creates some resistance to feature learning, right? But for the record holders means that are able to give you the best answer, best accuracy, based on the standard international accepted data sets, right? And also ImageNet and also segmentation are convolutional nets. So you're using convolutional neural nets able to give you fantastic results, both based on either the ImageNet or on the application called semantic segmentation. And the method that's able to hold the world record is actually based on convolutional neural nets. At the same time, other than computer vision, there are some researchers using deep learning in natural language processing. Understand a normal speech, right? Please open the door. Please give me a cup of coffee. Please call call Mr. Yong, for example, or EJ Ahmad, right? So that is what you call by natural language processing, to understand from that and then do the right thing. But this is not so simple. Why? Because we have these different people. Even though if you look at it from the point of view of English, there are various people who speak English in a slightly different way, right? But of course, there's one good area of work which I hardly see. At least maybe I've not been following the area very closely. The whole world is spoken in English, but what about Malay? Or even Chinese? Maybe not Chinese. I think the Chinese in China would actually have done it. So come back to Malay. If Malaysians do not tackle Malay speech recognition, who else will do it, right? You won't find any other people doing it. So that's the one area we can actually we try to excel, at least internationally and also locally, looking at Malay language processing using deep learning, for example. Then there's also another one, which is deep learning or feature learning in applied mathematics. So this is actually looking at the other area. So this is something that, just to give you a flavor, flavor of the how wide the application is in terms of deep learning. So maybe I'll show you basically this is an interesting sort of a map of the machine intelligence. So we have your shallow. These are all the what do you call? These are all the different methods in AI. On the right hand side are the similar methods in deep learning using again machine intelligence. These are all the shallow ones, and these are all the deep ones. So now, right? So these are the deep methods, and these are the shallow methods. But look at it. The one in yellow here are your neural network base. So neural networks can have also autoencoders, which is a shallow type. You also have autoencoders in the deep side, right? Of course, we have the perceptron, our friend perceptron. At the same time, if you use probabilistic methods, you can also have your deep, right? DBN, DBM, the Bayesian neural networks, right? And this is based on the probability model. But at the same time, you also have your shallow methods. So these are basically what it says is that the neural networks can have both shallow and deep. So do your probabilistic models, your shallow probabilistic model, and so your deep models. Then if you further break it down, into supervised, unsupervised, and supervised, right? So here will be your supervised methods in the shallow domain. This will be your similar area in deep domain. So some at the middle here will be your unsupervised, consisting of both your neural networks and your probabilistic models, covering both your autoencoders, your DBN, your DBM, your Bayesian, sparse coding, and so on and so forth. So common deep networks, just to give you again some of the common names for your some of the models that is popular in your deep networks. Of course, I have a caveat here. This is not exhaustive, as I said before. I can change tomorrow. Now, deep learning is a fast-growing field, and new architectures, variants will appear frequently. We will examine the 4 major types, right? So this is actually to show you some of the architecture and how different it is from the earlier models we've seen so far, the more shallow ones, right? So you have your, first of all, your recurrent units. So again, I think this one we've explained, just we finished the lecture on that, so I won't go too much on that. So this is the, so basically what it's saying is that your recurrent units also can be deep, can also be modified to become deep recurrent units, right? And this is something that some of you may be thinking of doing. I had a student looking at this 2 years ago, looking at the LSTM, long short-term memory, to actually look at the stock market prediction. Right? We actually use that and able to show you quite interesting results. So the LSTM can learn very deep learning tasks. They require memories of events that happen. This is a time series, thousands or even millions of discrete time steps ago. So LSTM works even when there are long delays, and it can handle signals that are a mix of low and high frequency components. Right. So this is your. So some of you might want to consider doing this, especially if you're doing time series forecasting. Autoencoders. I have one student for RMH looking at using autoencoders. Actually, 2 students, over 2 years, looking at autoencoders to actually detect defects in the image. Right? If you have manufactured products, so how do I identify very small defects? So they actually use autoencoders. So autoencoder, as the name suggests, consists of 2 parts: encoding and your decoding. Right? So the autoencoder is a type of neural network where the output layer has the same dimensionality. Over here, 245, 245 as the input layer. So output layer has the same dimensionality as the, so the flip is a mirror of the encoder layer. So in simpler words, the number of output units in the output layer is equal to the number of input units in the input layer. So basically, the autoencoder replicates the data from the input to the output. So it repeats, it sort of copies the data from the input to the output in an unsupervised manner. And it's therefore sometimes also in some books and some papers also referred to as a replicator neural network. So this is more details of the autoencoder if you're interested. So an encoder part is a feed-forward, fully connected neural network that compresses the input data over here into a latent space representation and encodes the input image as a compressed representation in the reduced dimension. You can see here, this is the first layer where your inputs are coming in. So it actually compresses it and reduces it in a smaller dimension. Right? So basically, the compressed image, as you may realize, is a distorted version of the original image. So now it's smaller. Of course, it will be distorted. Now the code here at the center here is a part of the network that contains a reduced representation of the input that is fed into the encoder. So now, after this, this will be will capture the information from the encoder side, and it will be passed to your decoder to give you some relevant outputs. So the decoder is also a feed-forward network like the encoder, and a similar structure because it's a mirror image of the same architecture as the encoder. So this network now, the only difference is that it is now responsible for reconstructing back the input back to the original dimensions of the code. So basically, this one will actually capture or actually compress the information here into a form, and then this will now and compress it back. We reconstruct back, right, the information here to the output, right, original dimension of the code. So, okay, this one actually explains to you the various types of how the actual encoder works. First, the input goes to the encoder, where it's compressed and stored in the layer called the code. Okay, right, compresses it, as you go layer by layer. Of course, this is only one example. I'm not showing you what I call 3 layers for the actual encoder, and also similarly 3 for the decoder. Of course, if you want to talk about deep, this will be many layers. So if you imagine, if you have a normal good enough picture of an object, what size are you familiar with? Say 100 by 100 pixels to represent a small image. So this will be 100 by 100 will be 100 multiply 100 squared number of inputs. So you can imagine the number of calculations you need to have, at least for the input layer, first layer. Then you get many layers here, right? So depending on your architecture. So again, as I said, there's a lot of computation going on. You need to do a lot of calculations before you come back to this part here. Of course, there's also, you need to also identify what is the optimum size of your coder, this level here, before you replicate back over here, reconstruct it back to the picture over here of the output. Right? So then the input will get compressed and stored in the code layer. Then the decoder will then decompress back the original input from the coder. Because you want to go objective of the encoder, so get back. So they will extract all the relevant features or details from your input picture. Now note that the decoder architecture is a mirror image. As I said, the flip is a mirror image of your mirror architecture of your input layer. Right? But it's not a requirement. What is typically the case. So it's not compulsory, but it's actually normally done, right? So the only requirement is that dimension of the output. Now this one, the only requirement is that this final layer here must be the same as this. So in between here may not be the same as here, but this one must be the same, so that you get back the same size of your input image. So of course, there are other types of autoencoders. Your conventional autoencoder, your variational autoencoder, your denoising autoencoder, and your deep autoencoders. Right. So this is an example. If your input is like this picture here, right, I will clean up for you. Right. Output is from here. You can then this is a denoising autoencoder. So your objective, your function of this autoencoder is to denoise, take out all the noise from here, then give you a clean image. So later on, maybe after this, you can then do another layer or do another deep network to actually recognize the numbers here. Now, of course, you have your convolutional neural net. I think we'll come to this in the next lecture. We'll go into more details of this, right? So, of course, there are actually the beauty of the advantages or attractiveness of the convolutional neural net is that they are used in many practical applications, image recognition, speech recognition, especially Google's and Baidu's photo taggers, has also won several competitions, right? In recognizing face, recognizing traffic signs. They are applicable to every data where nearby values are correlated. Now, they are one of the few models that can be trained purely supervised. Now, so you can see here, it's basically very complicated type of network. So what are they good at? What are what do you call it? CNN good at? You can see it's a list of them, right? So these are it's a list that they're actually I think they're only done in the 6-7 years ago, and they're doing quite well. They're holding the list that of course is also increasing. Maybe some of you actually will contribute towards that list. Traffic sign, one example, traffic sign recognition for the German traffic sign recognition, getting 99.2% accuracy, pretty good. Recognizing house numbers, right? This is about 94%, pretty good for Google. And then object recognition, right? So this is basically trying to impress you that what they're good at, right? So now if you have a test image here, when you have a trained deep neural net, right? You can also tell you that it will tell you that this picture here belongs to this class. So this is the right answer. You can see here, they are actually tell you that this picture belongs to this class. So from here, maybe put another layer to tell you this is a picture of a pumpkin, for example. This picture of a dog, right? So you're trained with different types of dogs and also different orientation of the dog. Okay, we will give you good answers. This was actually done about 9 years ago by Hinton and gang. Popular, these are the popular CNNs. Of course, this list is actually outdated, but this will give you an idea. Some of the things some of you will be using, like VNet, LANet, XNet, VGGNet, ResNet, so on and so forth. Now, what about semantic segmentation? Semantic segmentation basically is to recognize regions of similar, what I call similar color, or similar belong to similar objects. Right? So this will be a picture of a sky, picture of a tree. This region is picture of a grass, and this region is a grass, and this region is a cow. So from that, you can then extract a picture of a cow, right? By doing from this segmentation, you do background subtraction, right? So this one actually uses a sliding window. So we actually move it one by one, right? Through to your CNN. So you slide your window, moving it your window for this picture, right? You slide it, moving it to the left to right, and then top to bottom, and then using your CNN to classify. This area is a cow, and this area, of course, is recognized as a grass. This was done in 2014, 2013. Now, for the fully convolutional network, again, for semantic segmentation, you can see here, I have many layers, and then these are my convolution layers, and then it will predict for me where is the output. Okay, a bit of advantage before we stop. So it has all the advantages that it does all the feature extraction. So you don't need to do any engineering features. Moving towards raw features, better optimization, a new level of noise robustness, multitask and transfer learning, better architectures. Challenges before I stop. It needs a large data set. So unless you have a large data set, your network will not be able to give you good results. Now, because you need a large data set, the training time is usually significant, right? And the scale of the net weight is important for performance. So you need to be careful with the networks weights. Now, when the features are of the same type, it's not a problem. But when the features are heterogeneous, like what we had before in your EBN, right? Your color can be 1 to a few thousand, whereas your curvature can be only from 0 to 1. So this can be updated. The parameters are hard to interpret, although there's progress made to actually interpret the parameters. And hyperparameter tuning is non-trivial. It's not an easy problem to tune your parameters that you use to get optimal results for your network. So I think we just nicely come to the end now. So in this particular topic lecture, we introduced to the concept of deep learning, and we spent some time looking at the motivation and the challenges of deep learning, both from the practitioner point of view as well as the theoretician point of view. And in the last couple of slides, we look at some of the more common deep learning models. Of course, there are more than that, but these are the more common ones. And then also we spend some time looking at some of the interesting applications of deep learning. So in the next lecture, we will come back to looking at in more details. What does it mean to have a convolutional network, and how does a convolutional neural network, the deep convolutional neural network, does its job, right? So we'll end here for today. Before we go off, are there any questions? Okay, if not, have a nice weekend. I'll see you back next week. Bye-bye.